We spent a couple of days now talking about photon theory and the photoelectric effect. We learned that Hertz discovered the photoelectric effect 130-ish years ago. When he discovered it, he noticed that when light of whatever frequency strikes a piece of metal, that sometimes an electron was ejected. So light or EMR in general would cause sometimes an electron to be ejected. Now, he found that when it wasn't ejected, or at least he hypothesized that when it wasn't ejected, that it was because there wasn't enough energy in the light. We needed more energy, right? So where do we get more energy from? If we're not emitting electrons, we need more energy. Hertz said we're going to get more energy from more light, right? And that doesn't mean necessarily brighter light, although usually it does. It could mean shining the light on the metal for a longer period of time. Bottom line is, we're going to get it from more light. But he was wrong, because observations that were made with the photoelectric effect for almost 20 years following that didn't support that hypothesis. If we had a certain kind of light that wasn't causing photoemission, that wasn't causing electrons to be ejected, then it didn't matter how much of that light we had, and it didn't matter how long that light shone on the metal for. Okay, it didn't matter. If light didn't cause it, then that light wouldn't cause it ever. So more light didn't give us more energy. Let's fast forward now to Albert Einstein. In 1905, he said we're going to get more energy, not from more light, but rather from higher frequency of light. That worked. Einstein said that the energy of a photon of light, remember what a photon is, a quantum of energy? The energy of this photon of light is related to the frequency and therefore related to the wavelength. So if we increase the frequency of light, we go from visible light to ultraviolet, or we go from infrared to visible light, or we go from visible light to X-rays, then that increasing the frequency increases the energy. And increasing the energy gives us more chance of releasing this electron from the atom. Okay, this worked. Now, because a certain frequency won't cause an electron to be ejected, but certain higher frequencies will cause electrons to be ejected, there must be a cutoff point for frequency at which electrons begin to be ejected. What do we call that cutoff point? What do we call that threshold where electrons begin to be ejected? Yeah? No. What do we call the frequency that is the threshold at which electrons begin to be ejected, Jacob? Yeah, we call it the threshold frequency, the minimum frequency of EMR necessary to eject the electrons. If we're above the threshold frequency, electrons are ejected. If we're below, then nothing happens. We're going to say that if the frequency of the EMR is greater than the threshold frequency, then we're good to go. Electrons are ejected in a 1-to-1 ratio, right? 1 photon causes 1 electron, 1,000 photon causes 1,000 electrons. But if the frequency of the EMR is less than the threshold frequency, then nothing happens, no matter what, ever. No electrons will ever be ejected, no matter how much of the light we have, if we're below the threshold frequency. What if we're way above the threshold frequency? So the frequency isn't just above the threshold frequency, it's way above the threshold frequency. We're still going to get electrons ejected in a 1-to-1 ratio. But what do we know about those electrons? What's special about those electrons that are ejected still as a 1-to-1 ratio, Hugh? They're more energetic. They're going to have more energy. They're going to be moving faster. So if the threshold frequency, I'm going to make up some numbers here that aren't going to make any sense in terms of actual frequencies, just simple numbers, just again for simplicity here. Okay, the threshold frequency is 5 whatever. 5 hertz, 5 whatever, okay, 5 units of frequency. That's the threshold frequency. If I have one photon that has a frequency of 4, nothing happens. If I have 1,000 photons that have a frequency of 4, nothing happens, no matter what, ever. If I have one photon with a frequency of 5, then 1 electron is ejected. If I have 1,000 photons with a frequency of 5, then 1,000 electrons are ejected. If I have one photon with a frequency of 9, then 1 electron is ejected. 1,000 photons with a frequency of 9, then 1,000 electrons are ejected. What's the difference between those electrons that were ejected by the photons that had a frequency of 9? Same number of them, but they're more energetic. They're moving faster than the electrons that were ejected from the photon that had a frequency of 5. Laura, you got a question there? Okay. Does that make sense? All right, we talk about threshold frequency lots, but every once in a while you see a question that talks about lambda max, which is a threshold wavelength. But that's not a minimum wavelength that's necessary to eject the electron. That's a maximum wavelength. So if the wavelength of EMR is below the maximum wavelength, electrons are ejected. If the wavelength is above the maximum wavelength, then electrons aren't ejected. You need to be below the frequency, you need to be above the wavelength, since wavelength and frequency are inversely related to each other. All right, if we talk about energy of a photon equal to HF equals hc over lambda, then we can also talk about another term, work function, which is the minimum energy necessary to eject an electron. If energy is HF, then minimum energy is H times minimum F, minimum frequency, or hc over lambda max. Work function can be in joules or electron volts, although occasionally we need to convert it to joules. We can always convert it to joules if we want, but occasionally we need to convert it to joules, and you'll see when that is in just a second here. We had another term called stopping potential or stopping voltage. That was the potential difference required to stop an electron once it's been ejected. The photoelectric effect has already happened. The electron has been ejected because the light had a frequency greater than the threshold frequency. The electrons left the atom. Okay, Elvis has left the room. The electron has left the atom. We want to stop the electron dead in its tracks. And there's a whole bunch of reasons why we might want to do that, including measuring some of the properties of the metal that ejected the electron, maybe the threshold frequency, the work function, so on. You'll see that in a little while here today. Bottom line is we're stopping the electron with a potential difference. Just like we can speed up a charged particle with a potential difference, right? Anytime you have a charged particle that you're speeding up or slowing down, whether it's in a context of the photoelectric effect or any other context, then what we want to do is a conservation of energy analysis. It starts with the electron, when it's been released, starts with kinetic energy. We're going to call it 1/2 mv max squared because we don't know exactly how much kinetic energy it has when it's released. All we can do is predict the maximum possible value that it has. Starts with kinetic energy after it's been released, and that kinetic energy gets converted to potential energy. So we're going to say kinetic equals potential, just like you'd have if a car was going up a hill to the top of the hill. The kinetic energy at the bottom of the hill would end up equaling the gravitational potential energy at the top of the hill. Now we're going to tack on a little EK onto the front of this, but really it still boils down to the law of conservation of energy. Finally, here's the big one that relates to conservation of energy. And unfortunately, the one that's not on your data sheet, despite the fact that we use it the most, this is the one that you would have used on page 719 of your homework for the most part. This says HF, which is the energy of the photon that strikes the metal, the initial energy in this whole deal, HF, is equal to the kinetic energy of the ejected electron, the final energy in the whole deal. Initial energy equals final energy, almost. Initial equals final plus whatever we used up in the process of ejecting the electron, which is the work function. So we're going to say that HF is equal to EK max plus W. The reason that that's such a big, important equation is because we end up using that so often as a result of being able to replace HF with HC over lambda, W with HF0 or HC over lambda max. And replacing, at least the possibility of replacing EK max with 1/2 mv squared or QV stop. One final little thing before we check over our homework here. I've told you that most times it doesn't matter whether you use joules or electron volts. Pick one. Pick whichever one is convenient for you, most times. But every once in a while, we have to use joules. Can anybody tell me when we must use joules? We don't have any other choice. Yep. Good. Whenever we're using 1/2 mv squared or QV stop, we've got to use joules. Now, if you're just saying HF is equal to EK plus W, you can use electron volts. Okay, EK doesn't have to be in joules, but if you're introducing 1/2 mv squared or QV stop, it does have to be in joules. If that confuses you in the slightest, then here's what I want you to do. Always use joules. Just, you got electron volts, convert to joules, and then just go with joules, because that always works. Okay, electron volts usually works. Joules always works. All right, we had 3 sets of homework last night, 3 sets of questions for homework, page 716, 718, and 719. Were there any issues with 716 before we move forward here? No? Okay, any issues with 718? Yep. Question number 2? Yep. Number 1 says light of wavelength 480 nanometers is just able to produce photoelectrons when striking a metal. What's the work function of the metal? All right, so we have a wavelength here clearly, right? And that's the wavelength of the incident light, the incident photon. We know that that wavelength, a lot of times we're given a question that says, here's the wavelength of the light. We just call that lambda. In this case, we're going to call it lambda max, the threshold wavelength. And the reason we're going to call it the threshold wavelength, even though the incident light isn't always the threshold wavelength, is because we're told that it's just able to produce. It's just barely able to produce. Okay? Just able to do something kind of infers the word threshold. Okay? So we're going to say the maximum wavelength or the threshold wavelength is 480 nanometers, which we're going to replace the nano with times 10 to the minus 9 meters. So we're not going to make it 4.8 times 10 to the minus 9. We're going to say 480, that's what we started with, and replace just the prefix nano with 10 to the minus 9. That's the threshold wavelength. We want to find the work function. That's all we got here. So what we're going to do in this question is just simply say W is equal to HC over lambda max. That make sense? Makes sense why that's the threshold value? Laura? Okay. Now, which value of Planck's constant do you want to use? You use whichever one you want. The joule seconds or the electron volt seconds one. Since our answer is in electron volts, we're probably going to go with the 4.14 electron volt seconds one. But if you're uncomfortable with when to use joules and when to use electron volts, just use the joules. Get an answer in joules and then convert it to electron volts when you're finished. Okay? By the way, when you look on your data sheet, you're going to see an equation for the threshold, sorry, for the work function. And I think on your data sheet, it just says W is equal to HF0. I don't think it says HC over lambda max, does it? But if you look, where is it? Right beside it, you see E is equal to HF equals HC over lambda. That's on your data sheet. So if you see W is equal to HF0 and E is equal to HF, HC over lambda, then I think we can all probably figure out that W is also equal to HC over lambda max there. Maybe make a note of that in your data sheet and then just remember that come test time or come quiz time tomorrow. 2, is that okay then? Okay, number 2, blue light of wavelength 410 nanometers strikes a metal surface. Here's the work function. What's the energy of the emitted photoelectron? All right, I'm glad we did both of these questions, actually. I'm glad that you guys asked me for both of them because I want to distinguish between the two of them here. Now we have a photon that is a wavelength of 410 nanometers. We're not going to call this one the threshold wavelength. How come? How come this is lambda max and this isn't lambda max? Nick? That would be like more of a threshold energy, okay, work function, the minimum energy necessary to reject the electron. So just because we have that work function doesn't tell us that that's not the threshold wavelength or the max wavelength. Yep. Yeah, in the first one, it's just able to produce. Here it produces it, but it doesn't say it's just able to produce it. Maybe we're way past the point of producing it. Maybe we're not. Maybe it does correspond to the threshold wavelength. Maybe we are just able to produce it, but it doesn't say that. So we can't assume that it's the threshold wavelength if it doesn't say that. Okay? So we're going to make that lambda instead of lambda max. We're going to make the work function 2.10 electron volts, and we want to find the energy of the emitted electron. What kind of energy does the electron have once it's been ejected? What kind of energy does anything with mass have once it's been ejected? Kinetic energy. So we're looking for EK max of the electron, right? Now we could say EK is equal to 1/2 mv squared. That doesn't look like it's going to work. EK is equal to QV stop. That doesn't look like it's going to work. I told you guys yesterday, if you can't come up with an equation pretty quickly for one of these problems, then use that one that's not on your data sheet. HF is equal to EK max plus W. Let's replace HF with HC over lambda equals EK max plus W. Let's plug in some numbers here. What value of Planck's constant do you want to use here? We got our work function in electron volts. Can we keep the electron volts, or do we need to switch to joules here? Yep. Yeah, I can keep electron volts here, right? Could I switch to joules? Sure, I can always switch to joules, right? That always works. But because I'm not using 1/2 mv squared or QV stop, EK I'm using, but not a QV or 1/2 mv squared, then I'm allowed to stick with electron volts. Okay, but if that confuses you, then just switch everything to joules. It'll be fine. Just a little bit more work, that's all. Okay, so 4.14 times 10 to the minus 15 electron volt seconds times 3 times 10 to the 8. Divide it by 410 times 10 to the minus 9 equals EK plus 2.10 electron volts. Okay, listen, for me, I like to use electron volts when I can because sometimes it saves some work. Okay, but don't be lazy. Don't get lazy on this, okay? Don't use electron volts just because you want to save some work. If you don't really understand when to use joules and when to use electron volts, then do the extra work and get it right, as opposed to saving yourself some time and possibly getting it wrong. Yep, okay. Work is energy, yeah. Oh, you mean like, what do you mean there? Yeah. Okay, so in physics 20, you learned work is equal to change in energy. It's similar here, but it's not exactly the same thing. We're talking about a work function specific to the photoelectric effect. And it is the energy that's used up in ejecting the electron. So in that sense, it is a change in energy still, but it's not like an FD kind of change in energy. So don't start setting the work function equal to F times D or anything like that. Okay, two separate topics really. Related, but you're not going to put the two together. All right, let's find this. 4.14 times 10 to the negative 15 times 3 times 10 to the 8 divided by 410 times 10 to the minus 9. Now let's subtract from that 2.1. We get 0.929. Yeah, 0.932. What did you guys get? Anybody else get 0.929? Okay. I don't know where they get 0.932 from. Okay. We're going to say we're correct by democracy then, right? We all agree that it's 0.929, then that's what we're going to go with. All right, finally, question, page 319, 719. Pretty sure that we're going to have a couple of issues with this one. You know what, let's take a look, let's take a look at 2 and 3. Does that work for us? 2 and 3? Question number 1, we're looking for, you know what, let's set up number 1 as well. Question number 1, here's the kinetic energy of the ejected electron. How fast is it moving? All we're going to do there is say EK is equal to 1/2 mv squared, right, and solve for V. You get 4 point something what? Times 10 to the 5? Did you convert joules to, electron volts to joules? Okay, there's the thing, right? Remember what we said? You can use joules or electron volts almost whenever, but as soon as you're using 1/2 mv squared, you've got to use joules, right? Make sense? So other than that, you're probably good there. Carrie? Yeah, a photoelectron is identical to an orbiting electron. It's just been ejected from the atom. So it has all the same properties. Whenever you hear photoemission, that means an electron's been ejected. Whenever you hear the term photoelectron, it's just, usually I say an electron that has been ejected. Well, it's shorter and more efficient to say a photoelectron, right? So I don't usually use that term, but in the end, it means the same thing as what I say when I say an electron that has been ejected. Yeah. You know what you do? You do multiply, but I would prefer, to be honest, to do that ratio thing. 1 electron volt over 1.6 times 10 to the minus 19 joules equals 2.1 electron volts over x joules. And then we just cross multiply. And when you cross multiply, turns out, yeah, you multiply them, right? But for me, like I'm brutal with remembering, multiplying and dividing and whatever. I'm better at figuring things out than remembering things. Certain things we got to remember, but my mind works better by remembering only the things that I have to remember and then figuring out the things that I don't have to remember. All right, let's take a look at question number 2 now. And question 2 and 3 pretty much go together, right? What's the kinetic energy of a photoelectron that's emitted from a cesium surface when we have this light here? Let's use our HF is equal to EK max plus W equation. Let's replace it with HC over lambda because we have the wavelength of light. This is not the threshold wavelength. It doesn't say that this wavelength barely emits or it just emits. Like, we may be at the threshold wavelength here, but we may be way below the threshold wavelength as well. So we can't assume it's the max wavelength of the threshold wavelength. They have an answer in electron volts here, but since we're going to use that to find the speed later on, I think I want to go joules right now. Okay, I think I'm going to go with joules right now. 6.63 times 10 to the minus 34 joules seconds times 3 times 10 to the 8. Divided by lambda, which is 400 times 10 to the minus 9. Equals EK max plus, what's the work function for cesium? I think it was on table, it was on that table that we saw yesterday. Yeah, they will for sure. As opposed to being in a table like it is for us right now, it's probably buried somewhere in a page of information that says use the following information to answer the next question. But it'll be there. You just have to be able to find it. Oh, absolutely, absolutely. And so giving you the kinetic energy or the speed of the electron to find the work function, absolutely. That could happen, yeah. So just solving for a different variable there, right? Who has the work function there from that table? 2.1 electron volts, thank you. So Let's calculate the, oh, sorry, wait a second here. If we're going to use 2.1 there, then we better use our 4.14 value, right? Okay. So it turns out I'm going with the electron volts after all. Okay, that's what they have my answer in number 2 as. Then I'll worry about converting it to joules. So let's say 4.14 times 10 to the minus 15 times 3 times 10 to the 8 divided by 400 times 10 to the minus 9. We get 3.105. Let's subtract 2.1 from that, and we end up getting 1.005, or EK max is equal to 1.01 electron volts. There we go. That's the answer in the book. Now, we want to find the maximum speed. We could have just subbed in 1/2 mv squared right there, right into that equation, did it all at once. But since we were looking for the energy and then the speed, we're probably going to now just say 1/2 mv squared separately. Comes a question like question number 1 then, right? 2ek over m. But, Nick, what do you got to remember to do? Yeah, now that we're using 1/2 mv squared, or if we were using QV stop, then we've got to be in joules. Use the unrounded number here. So your joules are going to be almost 1.6, right? Plug that in, solve for speed. Now look at that. We learned in Unit 2 that the speed of a charged particle is usually in that 10 to the 5, 10 to the 6, 10 to the 4 range. Not always, but usually. What can't it be greater than? 10 to the 8, 3 times 10 to the 8, right? A lot of people will get a number that's 10 to the 10 for this. What have you forgotten to do if you get 10 to the 10 or 10 to the 11 for this? Square root it. And that's a pretty common mistake. But the nice thing about it is, okay, you should be able to catch that mistake if you forget to square root it, because you get a number that's impossible. All right,